Welcome to this video lecture on transient conduction. We're going to talk in this lecture about the lumped capacitance method. In our last video lecture, we showed some simulations where we were heating up different materials. And so I want to start this one with a review question / a thought question to motivate today's discussion. So if you were heating up two different materials, oak and steel, for which material would the approximation of uniform temperature be most appropriate? Assume everything else being the same. Think about that. I'm going back to this simulation that I showed in my last video lecture, but I've frozen that simulation at 1.81 hours into the simulation for both the oak and the steel. The oak is on the left and the steel is on the right. So they've both been given the same amount of time to heat up. Remember, we started at 5 degrees C for each of these systems. So if you notice, there's this significant amount of curvature still in the oak wall, whereas the steel looks pretty flat. These two can be distinguished by their thermal diffusivity. So the thermal diffusivity for the steel is roughly 70 times greater than that of the oak. We defined thermal diffusivity as K over rho Cp. So this depends in large part to the thermal conductivity. You can think of this alpha, this thermal diffusivity, as the term that helps balance out the curvature with the change of temperature with respect to time in this PDE. So again, this is a form of the heat equation under these specific circumstances, and we just lumped together this parameter alpha. So if you notice, we're right at about 17 degrees maybe with the steel, and if we took an average of the oak, we're probably, in that range of maybe 17 or 18. So they've both been heating up at roughly the same speed. However, the oak has much more curvature. So one way of thinking about that is that these greater temperature profiles develop in the oak because that has to be the driving force. So because it has a much lower thermal diffusivity, it needs that much greater curvature in order for heat to propagate into our solid. Whereas the steel, with the much higher thermal diffusivity, that's balanced out by a much flatter system. So our second derivative with respect to temperature is very close to zero, but we still achieve that same change in temperature with respect to time, or roughly the same for the two systems. So this alpha is really going to help to define the curvature as these processes heat up over time. So if you think about this, there's kind of a lot of information required to describe what's going on in the oak wall. Whereas in the steel wall, we're just looking at a flat, boring line at this particular snapshot in time. So what that tells us is, maybe we really don't care all that much about how the temperature changes with respect to space in the steel. So we could make an approximation that the temperature with respect to space in the steel is just constant. That will allow us to solve the problem easier, and we could focus on just how temperature is changing with respect to time. So that particular approximation, where we're assuming uniform temperature all the way through our solid, is known as the lumped capacitance approximation. We're just sort of lumping all the temperature into one block for the entire solid. So if we did make that approximation, I have another thought question. Which version of the heat equation are we solving in that particular instance? Feel free to pause and think about it if you'd like. Okay, so this one is actually a trick question. So we don't care about how temperature is changing with respect to Y and Z because it's a plane wall system. We're not thinking about generation. And we're actually, if we make the approximation that temperature with respect to X is just constant, then actually this term goes away, and we're left with kind of a meaningless thing that dt equals 0, which actually is not the case. So the heat equation kind of goes away because if you remember, the utility of the heat equation is we want to solve the heat equation when we care about getting the temperature profile with respect to space in a solid. So because we're not concerned about how temperature varies with respect to space in our solid, the heat equation just kind of goes away. We don't use it at all. It's not valid. So heat equation does not apply. And what we would actually want to do is execute an energy balance assuming uniform temperature in the solid. So here we could consider convection, radiation, and generation happening at the boundaries. So put another way, if we took our wall and just assume that this is our control volume, And this could be generating. So we could have, I'm just going to use an E dot term here instead of the volumetric generation term. It could be generating, it could be convecting, or it could be radiating. We could also have a constant flux coming into it. So if we did an energy balance, we would get our accumulation is equal to rho Cp times the volume of our solid times the change in temperature with time. And then let's think about this as a cooling process. So let's consider only out terms. Let's consider the flux as an in term. Okay, so in, we're going to have our flux coming in over the appropriate area. And then out, we could have convection. So we could have H times our surface area times the temperature of our solid minus T infinity. If it's radiating uniformly to all its surroundings, then we would have our sigma epsilon times area times temperature of our solid minus T surroundings to the fourth. And then certainly we could have our generation term. Rather than the volumetric generation term, I'm just going to use E dot sub G. So that's what our energy balance would look like, and it just sort of depends on which of these terms are we considering. So if we compiled our energy balance and did accumulation equals in minus out plus generation, then we would get our accumulation term equals the term that comes in from this constant flux minus convection, minus radiation, and plus generation. So that would be the basic equation that we're working with. So this may be difficult. Notice it's still an ordinary differential equation. It still could be difficult to solve with all of these different terms. So it's more useful to look at specific cases. So the first case that we're going to look at is the convection-only case, and we're going to go through a brief derivation of that. So if we looked at convection-only case, here is basically what our energy balance looks like. Our book uses the lowercase c instead of c sub p, but this is basically what we just derived if we only considered the convection term. So how do we go about solving this? So it's easier to put this into homogeneous form, and we can do that by making a small transformation of our state variable. So specifically, we can define theta, where theta is the temperature difference between our solid and ambient. So we're going to use this particular definition of theta here. We also want to define our initial theta. So this is a transient or a dynamic problem, so we're going to care about our initial condition. So if we care about how temperature is changing with time, well, we have to know what's temperature at the beginning of making whatever change you're making. So our theta I is equal to our solid initial temperature minus the ambient temperature. So if we make these substitutions of theta for our temperature difference, we get this form of the equation, which you can see is a fairly common form. We end up integrating and we get this form. So we can solve this, telling us how long it might take to get from some initial temperature to some final temperature. So we can solve it and keep it in terms of time. So this is really a useful equation to know how long does it take something to heat up or cool down when we're using this lumped capacitance approximation. Alternatively, we may care about how does the temperature evolve with time, so we can just rearrange this equation algebraically to solve for our temperature, and this is given in terms of our temperature ratio. But you could see with some simple reorganization of this equation, we could get pretty easily our temperature as a function of time. So if these are the particular circumstances, if it's a convection-only system, here's the solution. And in this case, you can sort of do just plug and chug here. You need to know how long the simulation is going and then some basic operating parameters of your system in addition to the initial temperature and ambient temperature, but then you've got your solution. And basically what the solution tells us is that if we are cooling, and let's say we have our initial temperature here, and we have our final temperature here, you see that the form of this solution is an exponential, and we would see that this temperature of our solid is going to exponentially approach our ambient temperature. And the same form of the equation would apply if we were doing this in reverse, if it's a heating process. And we have our initial temperature here and T infinity up here. So if we're thinking about this in terms of our energy balance, those terms might flip. Convection would be coming in rather than going out. But either way, the math ends up being the same. So we would expect our temperature to asymptotically approach that T infinity, to get exponentially close to it, and eventually sort of level out to be at thermal equilibrium with the surroundings. Okay, so this particular term tells us a lot about how fast this process is going to happen. And notice that the value of the convection coefficient is actually really important in this equation. If we lump those parameters together, rho v times c divided by h times our surface area, we get what is called the thermal time constant, or tau. So tau tells us a lot. If we lump all those parameters together, tau tells us how fast this process is going to happen. So here, this shows a process with a relatively lower tau. You see that the cooling happens faster, where if tau is bigger, because the system has a higher density or a higher volume or a higher heat capacity, or if it has perhaps a lower convection coefficient, things are going to happen more slowly, and you would get a temperature changing with time that looks something more like this top line here. So that thermal time constant is a really useful parameter. And notice here we are plotting the relative temperature difference. So this ends up being unitless on the y-axis. Okay, so that tau can be a really useful thing if you're concerned with the speed at which your system evolves. And tau is actually a really important parameter in all sorts of dynamic processes, which for the chemical engineers, you would cover that in your dynamic processes course, or if you're a mechanical engineer, you might cover that in some sort of dynamics course. For a dynamic system, tau is kind of a characteristic of your system that tells you how fast things are going to evolve with respect to time. Okay, so this is a really nice approximation. We found that for the steel wall, at least, we can find out a whole bunch of information, and we can get this down into an equation where you can just kind of do plug and chug. Just give me the parameters, I'm going to put these in an equation, and I can plot that equation and figure out how temperature is going to change with time. So because this is such a useful approximation, we're going to want to make sure we know when is appropriate to use it. So when can you use the lumped capacitance method? I'll go back to this example where we have a wall dividing two rooms, so room 1 on the left and room 2 on the right. So we really want to start thinking about this in terms of the relative speed, so that if you recall, the oak wall and the steel wall both heated up at approximately the same speed, if you think about average time of heating up. But what really will matter is whether is the relative speeds of the convection process happening relative to conduction. So let's think in terms of thermal resistances. So this is a transient system, so actually using the thermal resistance method as we have in the past would no longer be valid. However, there's another useful tool for using thermal resistances here. So if we divided the system, assuming that it's symmetrical, as if we had the same T infinity on each side and the same heat transfer coefficient, we could draw a thermal circuit just considering half of our system here. So let's look at the temperature at the center of this thing. We're going to have a symmetrical system, so we can do this kind of thing. So let's think about the thermal resistance through the wall itself, and then the thermal resistance associated with convecting back out into the ambient air of the room. So what will tell us if we can use the lumped capacitance method will really be the ratio of these thermal resistances. So if convection is the limiting process, or if it's going more slowly because it has a higher thermal resistance, well then we are going to see that balanced out by a higher delta T for convection. So if convection is the limiting process or the slower process, then this lumped capacitance method might be a good approximation. Because if this is the case, the delta T associated with convection will be bigger compared to the delta T associated with conduction, because this convection has the higher thermal resistance. And by comparison, the delta T associated with conduction will be smaller because that's coupled with the smaller thermal resistance of conduction. So if the delta T here is smaller, then that implies that perhaps you could get away with a lumped capacitance approximation, assuming that temperature is uniform. So let's try and formalize this a little bit more. So if we think about, again, now we're just looking at half of a wall system, so a half wall system here. So if we were to assume this is at steady state and do an energy balance at this surface, that energy balance would look like this. So we'd have the delta T from conduction multiplied by Ka over L, and we would equate that to the rate at which heat is leaving by convection. So we could look at the relative delta T's here, and we could figure out which process is happening, which process requires the larger temperature difference in order for that total flow of heat to remain constant. So if we were to rearrange this equation a little bit and look at, here's the delta T from conduction, and here's the delta T from convection, well, those would be set equal to the thermal resistances here. So if we looked at the ratio of the conductive thermal resistance to the convective thermal resistance, the A's eventually fall out of that equation and we can rearrange it. This becomes a unitless term, which we are going to define as the Biot number. So when the Biot number is very, very small, that implies that K might be really large, or H might be really small, or L might be really small. So that would imply that there's going to be a pretty shallow delta T through our solid, and that is shown here. So this line is a system that has a really small Biot number, whereas this bottom line is one that has a comparatively much larger Biot number. And it has this system with the larger Biot number also corresponds to the largest temperature difference in our solid. So if conduction happens really, really fast, as it does with this top line, then we can make a better approximation that the temperature is uniform for that particular solid. So this Biot number are going to be our test for how do we figure out if we can apply the lumped capacitance approximation. I want to emphasize that the thermal resistance method still does not apply if you want to quantify flow of heat. You can't use that method. You can't quantify the flow of heat using the thermal resistance method when you have a transient system, because remember, a lot of that heat is being absorbed by the system as you go along. However, doing this steady state analysis to figure out the Biot number tells us a lot about how we could more effectively solve that transient problem. Okay, let's look at this a little bit differently. So as a general rule of thumb, when the Biot number is less than 0.1, then the lumped capacitance approximation is a good approximation. So if this holds true, we can apply the lumped capacitance approximation. When this is not true, then we cannot necessarily apply the lumped capacitance approximation. Basically, it would tell us that the lumped capacitance approximation is a much worse approximation. And you can see here are some conceptual transient results here. So here in this solid with a Biot number much, much less than 1, this is another, actually this is a cooling process. So we're starting here and going down this way. But you can see as you go along in that cooling process, the system with the low Biot number, the temperature profile throughout remains pretty flat. Whereas on the far right extreme, as this process starts to cool, think of this is kind of like the oak wall. And this is like the steel wall, only we are cooling instead of heating in this particular case. But notice that the oak wall still maintains these really deep temperature profiles. So the lumped capacitance approximation would not be quite as good here. You may be wondering what this L sub C is. So L sub C is the characteristic length of your system. So that may vary depending on the shape of your system, and it's conventionally defined as the ratio of the volume to the surface area of your solid. So you can apply this to cylindrical systems or spherical systems. You just have to go about calculating that characteristic length differently. So this is a rule of thumb for knowing when to apply the lumped capacitance approximation. What we have covered so far is this convection-only case, and we came away with some really nice results from the convection-only case. However, if we have to consider those other terms, there are different solutions. So some of those solutions I wanted to cover briefly in this presentation. So remember our general case, we derived sort of our own energy balance there. That looks basically like this. We have our flux term, we have our generation term, convection, radiation, and then we have our accumulation term. So depending on which of these terms we can neglect and which we care about, you'll get a different sets of solutions. So if we're thinking of only a radiation system, as in we are neglecting convection, we're really solving this form of the equation, and the nonlinearity of that equation makes it a little bit more difficult to solve. So I'm going to jump to the solution. If we wanted to solve for time, knowing an initial temperature, it would look like this. So quite an involved equation, but it is just plug and chug. Another case would be if radiation is negligible and we're only considering these other terms. So we can consider flux, generation, and convection, but not radiation. Here's how the solution looks. So if we looked at our relative temperature profile, we see that it takes on this particular form. I'm not going to go into the solving of this differential equation, but just know that you could use this form for different combinations of those things. Notice these B and A parameters, those are defined as shown here. So you could just figure out what those are. And then notice that some of those parameters may go to 0. So for example, if we don't care about the flux term or the generation term, so here's the flux term, here's the generation term, B would go to 0, meaning this whole part of the equation would go to 0, and we'd be left with the convection only case. So this is a more generalizable equation if we can just simply neglect radiation. That's the end for today. In our next video lectures, we're going to talk a lot more about cases where you cannot use the lumped capacitance approximation. So when your BO number is too high, meaning that you really have to track temperature as a function of both time and space in your system.